Hey, this is G from Outlier Automation. Today I'm going to be talking about securing Ethernet-based communication in industrial networks. What are the pieces involved and what does that mean? First of all, what are we even trying to secure? What part of our network should we care about? So I have this diagram here, and you can see this is fairly complicated, but what I'm trying to show here is, if looking at the bottom, the PLC is the central of our network. There's actually many different connections to different devices or services on our network now that are Ethernet based. And there's multiple protocols that this could be communicating back and forth with our PLC. And this is just one PLC in a system. There could be many of them. This is kind of looks like the Purdue model, which is kind of the traditional model of what we think of the network in our control systems. But it's really becoming blurred, mostly because there's many different communication paths, and what we need to do or pushing forward with what our systems are getting as far as data acquisition, getting instructions from other systems, and basically enabling what we think of as Industry 4.0. But at the same time, we are creating many different paths for vulnerabilities, and all of these different protocols, whether it be MQTT, OPC-UA, any type of industrial protocol, or even HTTP through a custom API through other vendors. These are all kind of based on what is the TCP IP stack, either at the transport level or the application level of what we think of the TCP IP stack. What we have to secure is all of these connections, and we have to make sure that each one of these don't have vulnerabilities. And how we do that is through transport layer security. This is a protocol used across TCP, and it is common in web-based applications, but it also applies in the industrial space as well. Since we're using Ethernet-based protocols, we also should apply it here. And what transport layer security does, the basic concept is that it provides authentication where we know that both sides that are talking are who they say they are. Encryption, which hides the data from, if someone was able to look at what we were sending, that they can't just read it plainly. And then data integrity, which is that the data that we sent or intended to send was actually what gets received on the other side. Why does this actually matter though? One, in industrial networks, is that it will provide us privacy. So if you're thinking about a web-based application, out on a public network, one of the things that we typically care about is like credit card information or someone's public health information. Here we don't have quite the same types of concerns. In an industrial network, we'll probably have in a control system, trade secrets or commercial research. We could be handling the end customer's data or even government secrets. It also could be having impacts on financial forecasting or stock information for publicly traded companies. If the control system is not performing well, or is down, or has some information about increasing goods, that could be used to move stock information. In general, all the data that we're transferring back and forth is sensitive, and we want to make sure that the data that the endpoints, we trust those endpoints, and we're actually sending that data to who we think we are. The next is the integrity of the data. What if the code or the program that we are looking at is not actually what is running on the controller? Or what if those set points in the controller changed unintentionally or even maliciously? That could have personnel or environmental impacts. And we could also, if we lost data, that could impact our quality and actually disrupt the processes from running at all. So we want to make sure that the correct data is being seen by the control system itself, the operators, engineers, and even all the way up to the CXO level, is that the correct data is being used to actually make decisions. And third, compliance. So what I mean by that is regulatory or compliance of the law. So this is very common in life sciences or pharmaceuticals, automotive, or it could also have quality impacts such as semiconductor, where the process is extremely sensitive. And ultimately, as all industries are becoming more automated, this is going to become more and more critical. It might not be a law-based compliance, but it could be an internal compliance of the company itself, where it's hey, the data that we are handling, we know that we're handling it responsibly. It's not being messed with somehow. either intentionally or unintentionally, and that the performance and quality data that we're getting is something that we can trust and is correct. So TLS, how does it actually work? The main thing is that you have a client and a server. The server is going to have some type of information that we want to request or even talk back and forth. So a client would come and it presents a handshake that's like, hey, I want to talk to you and I haven't talked to you before. And the server says, okay, if you want to talk to me, then take a look at my certificate. And the certificate is basically a predefined file that has a bunch of information about how to talk to it securely. And then the client goes back to a third party called a certificate authority, or a CA, and says, hey, like, I don't know if I can trust this server, but you have looked at them before, or you're a third party. Is this legit? And can I actually talk to them and trust it? And the certificate authority says like, hey, I saw that I've issued this certificate before. You can trust me, and therefore you can trust the server. They are who they say they are. So then the client goes back to the server and says like, hey, the certificate authority said you're good, and I see in the certificate that you gave me this key that I can use to talk to you. But if you have the key, can you actually like solve this little riddle that is supposed to be with this key? So basically both sides generate a kind of a random message that says like, hey, if we both have the key, the right key, the end result should match. And if it matches, then we can go ahead and talk. And so there's this first part that says like, hey, let's authenticate. And once we've authenticated, then we can open up our secure communication channel. I mentioned the certificate. That's kind of the key part to setting up this authentication. What's actually in it? The first is that like information about who the server is, they actually are an entity that is real. That's where the concept of a certificate authority comes in. Think of the example of a public web. You could have like anyone in the world can throw up a web page, and they could be legit or not, or they could be impersonating some other legitimate company. So a certificate is actually like a third party that people pay that's like, hey, third party, Amazon, GoDaddy, whoever, I'm paying you to look at me and say that my web page is secure and actually like the data that I'm putting up there is real. The certificate authority is kind of like this standard location that everyone agrees is like, if this certificate's on there, that's like probably fine and you can trust it. That's a very key part of that, and I'll go into that a little bit more. The other part that's in there is that the certificates are time-based. They should expire some amount of time in the future and not infinite. If you had a certificate that was, from 10 years ago, that is probably out of date at this point. Like if a web page hasn't been updated in 10 years, especially with the way technology is moving, it's probably not legit. So this issuance date is for web pages has actually been getting shorter and shorter, because if some bad actor came in with an old certificate, they could actually fake authenticate with these certificates that really shouldn't be legitimate anymore. The reason why I highlighted this in a control system environment is that sometimes we can have control systems that are kind of like on what I would call an automation island, is a typical way to say it, is that they don't actually have any communication from the outside world, and you can have the time go out of synchronization or not even have a real time because it's just the controller running by itself. So this is a key part to think about in your certificates, is that if you're using them in a control system, you have to have legitimate time synchronization in order for these to work. And then finally, the public key that I mentioned earlier is that this is like, hey, if you want to trust me and authenticate with me, this is basically the encryption in order to decode the messages that we send. Okay, so I was talking a lot about example within a web page, like why would we be using this in a control system? I already mentioned that there's a lot of Ethernet-based communication, but like a real example here. So for example, in that handshake pair, the PLC could be the server, and you could have multiple types of clients. So it could be an HMI, it could be other machines that are running OPC-UA. You could have an embedded browser in specifically the example of a Siemens PLC. So someone wants to connect to the browser and see that the data is real. And then you could also have programming laptops or engineers connecting to PLC, and you want to make sure that the data that's being sent or changed on the program for the PLC is real. So that's all good. This all should be encrypted and use TLS theoretically. The one part of this that is kind of tricky is who is the certificate authority in the case of verifying that it's a certificate. So there's actually two different things, or two different ways you could do it. One is that it is the third party, like I mentioned before. So you could actually say like, hey, I have this new HMI connection. I'm going to go buy a certificate from, the internet, and like it's going to be independently verified. I'm going to load it onto the PLC and HMI combination. That works. That's fine. The problem is, it's not really a problem, but like if you don't want to pay for it, or you just have like one device that you want to set up, that might not make sense. It's enabling trust, but like maybe we don't care about anyone else outside of our local network. And in that case, you could use a certificate authority that is self-signed. That means that basically you are setting up and saying like, hey, I know all these parties involved. I'm just going to say like each side, you should trust each other, and I'm making a certificate for you. As long as the dates are legit, then that's okay. So in Siemens and TIA Portal, you can actually use the project itself as a certificate authority. And the first time that you load it, it will create that trust, and then going on, it will make it be encrypted communication. These are all kind of, I would say, new concepts if you're coming from controls engineering world. And these are aspects that are being brought into many different vendors. If you follow the Siemens platform, it's been evolving over TIA Portal version 17, 18, I'm sure more in later versions. And I think I would encourage you to start using the certificates and the TLS encrypted communication for all the reasons that I said before, is that like there are many different risk points. As soon as you get comfortable with certificates and Ethernet-based TLS networking security, I think that you'll really get a benefit out of it and really reduce the risk of cybersecurity incidents in your facilities. So good luck, and let me know if you have any questions on our YouTube channel. Please subscribe.